Okay. Okay, so last week we finished up 5.2 and y'all took a test over it. And so hopefully you got everything submitted that you need to submit in. So I don't guess there's a lot of sense in asking questions about older stuff since we've just taken a test on it. So 5.3, I believe 5.1, 5.2, we were doing functions and their inverses, and then we saw if they were one-to-one. I believe that was like the last thing we did in 5.2. So 5.3 is taking a little bit of a different direction. We're going to do exponential functions and models, and so they kind of start you off here with something that hopefully you're kind of familiar with. So here, talk about the change here. These are each going up by 1. These are each going up by 3. So they're increasing by a factor of +1 by +3. We talked a little bit about this. This is a constant rate of change. We call constant rates of change as slopes. So if I want to do my slope, it's the change in y over change in x. So I could figure out this is what, 3/1 or 3. So it's giving me a slope. So if I want to know what type of function this is, if I'm getting a slope, that should be an indicator that this thing has to be linear. So we're talking about a linear function. So I think we can fill in pretty much everything else. Y equals mx plus b. So that's the form it's in. And so if I want to fill in numbers, I know that's a 3x. My plus b I'm getting from this thing. My y-intercept is 0, 5. Gives me a 5 for my b value. And so maybe one thing to note is that we're adding the same quantity here. If we're adding the same quantity, this change is going to be the same. Similarly here, these each go up by 1. So sometimes they try to be tricky with their numbering and their x. Just trying to be kind of straightforward. We're just adding 1 each time to our x. It's not changing. But if we look here, if we tried to add a number, well, here would be adding 2.5 to get to 5. Here would be adding 5 to get to 10. So you could say that like plus 2.5 plus 5 plus 10 plus 20, right? We could do that, but it's not going to be a constant amount if we do that. You might notice that you're adding the same number or you're doubling it. So another way to think about this is you're multiplying it by 2. And if we think about these as multiplying by 2, you might notice each of these changes we can describe as multiply by 2. Okay. And so then I guess it begs the question, like, what sort of change is this? Well, you could probably look at the title of the lesson and figure out this is probably an exponential function. We hadn't really talked much about the form, but it's right down there. It is the y equals c a to the x. And now I want to talk about a little bit about how to like obtain these numbers, how to get the numbers. So we plug in 0 to our x, it's going to give us 5. But if we plug in 0 to our x, you might notice a to the 0, anything to the 0 is just a big fancy 1. So this is just a 1 here. So this will simplify out to 1. So what this number is actually giving us is our c value. So our c is our y-intercept. And then there's one other number we need. We need to know the base. And if you were to guess the base, there's only probably one other number on this paper you would probably guess. It is doubling, so our base has to be 2. And I'm supposed to have an exponent of x up here. I'm running out of paper almost. So the c, or the coefficient, would be 5, and then the base would be 2. And so we'll go over a few more examples on how to find the specific form of the exponential from the general form. We'll go into a few more examples in filling those numbers in. I was looking at this earlier, and I think I want to like throw a page at you a little earlier. So this is an exponential function, a function represented by f of x equals c a to the x. And so you might notice that our a has to be positive, so our base has to be positive. They're not doing negative bases. They're not doing a base of 1. 1 to the x is not a very interesting function. It's kind of a really silly way. We have 1 to the x, 1 to any number is just equal to 1. And so it's kind of a silly way to write the y equals 1 function. It's not a very interesting function. You can think about it, but they don't want to think about it here, basically, right? And c is greater than 0, so our coefficient is also positive. So they give you a few examples here. But if our base has to be positive, but if it is a fraction, right, between 0 and 1, so if it's fraction, we're multiplying by not a whole number like up here, but we're multiplying by a fraction. So if we keep on multiplying by, like, take a number like a half is a good number in here. If we keep multiplying by a half and a half and a half, you might notice this thing is going to get smaller and smaller, right? We're multiplying by a fraction, and so that is going to be exponential decay is what they're going to say. And if it's greater than 1, then we're multiplying by a number larger than 1. So that, like, kind of like the times 2 in the example. This is going to give us exponential growth. And 1, 2, 3. I believe it's on like the 4th page. I noticed there's a few things you might want to like just throw at you while we're here. Throw it a little earlier. But it says these things like if we have an exponential growth and decay function, hopefully you notice from these graphs, our domain is from what? Minus infinity to infinity. So there's no number that we can't like plug into these things, right? Basically is what they're saying. There's no sort of domain restrictions happening with our exponential functions. Our range, so you might notice our range does not go below the 0. And if you notice here, as we go off to the right, you might notice that there's a sort of asymptote sort of thing happening here. And our asymptote is going to be the horizontal asymptote of y equals 0. Same thing here, it's just going off to the left. So we have this sort of asymptote here. So I believe that's what number 2 says. We have an asymptote. Is that what it says? The graph is continuous with no breaks, so we don't see any breaks in it. The x-axis y equals 0 is a horizontal asymptote, and there is no x-intercept. It doesn't cross the x-axis, but it does cross the y-axis at the c, so we talked about that. That's going to be our y-intercept. If it's greater than 1, then it's increasing. If it's a fraction, then it's decreasing. That's what we just said. It is 1 to 1, so we can do a horizontal line test. We can do a vertical line test. It's 1 to 1, and it has an inverse. So I'll probably pass these back up in a minute. Okay. Find a function that models the following data. So I know this is the exponential section, but they're trying to make sure you can kind of distinguish between what you know and what you're learning, I think. So we're going up by 1 there. If we go here, the easiest way to describe this change is that's going what? Down 3 and down 3. And if we want a function that models this, is it going to be linear or exponential? I guess is my question.
It's going to be linear. It's y equals 1/3 x plus 10, right?
Yeah, not 1/3. It's going to be -3/1 would be our slope, right? Yeah. And so it would be a -3x, and then what? Plus 10 is what you said? And so it is linear. So we want to use linear function. The thing that indicates that it's linear is that this is addition, subtraction, this is addition, subtraction, right? As opposed to probably like this next one. Each one of these we're multiplying by what? 3 to get to the next one? And so if you're multiplying by 3, we want something that is exponential, like c a to the x. My c, I've kind of said it already, is coming from my y-intercept. So my c should be 2. And my a is a base of what?
3.
Yeah, 3 that we're multiplying by. And if you want to, we know how to plug things into functions. We could compute these things, and it might help you like see this sort of pattern a little bit. If we plug in 0 to our x, this thing is going to be nothing but 1, right? And we're going to be left with 2. If we plug 1 into our x, we're going to have 2 times 3 to the first will give us 6. If we plug in 2, we're going to have 3 squared is going to give us 9 times 2 will give us that 18. So each time we're adding another factor of times 3, right, is what's happening. Okay. So if they, maybe something to note, if we're trying to find exponential and they give us our y-intercept, it makes things a lot easier. And so we'll have an example here. And so not to get lost in function notation, but if I see this, I'm hoping you see that this is a x quantity, and this has to be a function value, so that has to be a y quantity. So if you want, I know sometimes this notation like confuses people, but we have the 0.06, we have the 0.13. Okay, so we want to find C and A. We want to fill in our variables. And so right away, I'm hoping you can fill in C. C should be what value?
The 6?
Yep, that's 6 coming from the 0, 6. And then we want to fill in A. And so we've already used this one. And so if we want to figure out A, if we've already used this one, the next thing to try would be to try this thing. So if we try this thing, my y is going to be a value of 3. I have 6 times A. I don't know what my A is, but my x is a value of 1.
Isn't x just half?
X is the one coming from here. Oh, wait, are you asking about A?
Yeah.
I think you're talking about A. Yeah, so we divide by 6. So we divide both sides by 6. 3 6 is equal to A. A is going to be 1/2. Absolutely. And then like coming back and filling everything in, we have our 6, we have our A as a half. And so we just need to fill in those two facts. Y equals 6 half to the x. And so that half is indicating that this is going to be an exponential decay. Which hopefully you notice because it goes down by half, right? When we go up by 1.
Does the x is it always growing? Like it's if you start, it starts at 1 and then goes to 2 and then 3 and etc. Like that's always the formula for this function.
They can give you the X kind of however they want, to be honest. I'm kind of like setting these up so it's really pretty to work them out, if that makes a little more sense. It's easier to plug in zeros and ones than other numbers, and so that's kind of why I'm giving you those numbers. These are those sorts of problems that only exist in the math book. You know, if you go out to reality, they're not going to be this pretty.
Okay. I like the math book world.
Yeah, it's sometimes it's a little easier when people set things up.
I feel like there's a lot of like linear things in the real world though, like factories, like producing stuff.
There are a lot of linear things. There's also a fair number of exponentials, but people like just like coming from someone who's taught this year after year, people do not understand exponentials nearly as like intuitively as they understand linear, which is kind of, you know, cause for concern with everything that's happening. But you right over there, Luis? Got a lot of noise in this line. Okay. Okay. So basically, if they give you a 0, you've got your C already. And if you need to find anything else, we've got to start plugging in other numbers. Now, they're going to give us this. And so it's still the same general formula. Y. If you want, you can rewrite these things as an ordered pair. Minus 9. Or what? 1, 1. And so we don't have a 0. We can't just jump into solving that C variable. Okay. But start with what you do know. So we can plug in these points into this formula. And so that is basically your approach. So if we plug in 1, 9, C, we don't know C, we don't know A. I know my X is going to be a -1. That's one thing I can talk about. The other thing I can talk about is 1, 1. So 1 to the 1. I haven't done systems of equations yet. So usually if you do systems of equations and you have linear sort of formulas, you're going to add and subtract them and do a canceling of variables. And this one is going to be a little bit different. We have a C here, we have a C here. And this sort of thing, trying to think of how to tell you without just giving it. If we have something like y over y or x over x, or maybe we'll do a different variable, b over b. So if we put the same variable over itself, that's going to make a big fancy 1 and sort of simplify it out and simplify out the variable, so it will eliminate a variable if we do that. And so that's kind of what I'm going to do with my C variable. There's probably a smarter way to do this. What I think I'm going to do is start with this one. And I want to divide it by this one. So this has 1/9 over here. This has CA to the -1 on this side. And to be honest, you can go either way with this. You can divide either way. There might be a few problems like this in your homework. So we have 1 and we divide it by 1/9. I don't know how you want to do this, but you're going to multiply by the reciprocal on top and bottom. You're going to multiply by 9 top and bottom. This 1 divided by 1/9, that side is going to be 9. If we look at this side, we have the thing I was talking about. We have C over C. The other thing I see here is my A. I have 1 divided by -1. And if we're dividing like bases, where these go back to our exponent rules, but we're doing what to these exponents? Have we talked about that? I believe we have.
Adding them?
If they're multiplying, you would add them. Since it's dividing, we're
Subtract.
subtracting these guys. So 1 minus a -1, or 1 plus 1, is going to be A squared. So if A squared is 9, then A is a plus or -3, but we know A is positive, so technically we can just like kind of jump to it's got to be the +3, right? So you should consider the negative for like a half second, and then you look at the definition and you say, hey, we don't use the negative, right? Okay, so we got A is 3. Let's use this fact. C, we don't know C. A is 3. So we've got this much filled in. So we've got to come back up. We've got to use one of these points to find A. You could probably already guess I'm going to go with that point. It's an easier point to solve for. So if we go back, plug these numbers in. I think what we get is 1 is equal to 3C. Or C is what? 1/3? And so if we want to fill everything in, y equals what? 1/3 is my C. My A is 3 to the x. So there's a few more steps involved if they don't give you that 0 right off. And there's a few different ways they can give you the points for these things. They can give you in like function notation. They can give you a table. My advice is to start out with what you know. Write out your points. Write out the general formula for the exponential. Plug in these points. It will give you 2 formulas. And then we're going to be dividing one by the other. What I would typically do is probably put the higher power of order on top, the higher power of A on top, so that when you end up doing this, you end up with a positive A. Find A, find C, we've done that.
Can I ask a question real quick?
Sure.
How are we getting A squared? I'm sorry.
This comes from this rule. If we have this over this, if it's a like base, we're going to subtract the exponent. So this comes from a of a1 minus the minus 1.
Okay.
So that's coming back from the exponent rules. Okay, so sample bacteria doubles in concentration each day. The initial concentration is 1.5 million bacteria per milliliter. Find a function that gives the concentration of bacteria after X days. And so they're trying to give you a exponential function in verbal form. And so there's two things you might want to notice. It doubles. And it says something about initial concentration is 1.5, and then they give us our units, right? Million bacteria per milliliter. And so we know it's exponential. And the key word that we know it's exponential is they're using this word, it doubles, right? And so if something's doubling each time, it's being increased by a factor of 2. And so this gives us the factor that it's increasing by. This is the initial concentration. Another way of saying initial concentration or initial amount, that's like talking about we've had this before, but that's like talking about your y-intercept, right? And so if this is my y-intercept and this is the amount that it's increasing, I think we have everything to fill out. That would mean my c has to be the 1.5 million. And then if it's increasing by doubling, my base here is 2. So then the other thing I need is my x variable in the exponent. So estimate the concentration after 4.5 days. And so this is the sort of thing we figure out our equation. And now if they give us 4.5 days, well, this is the amount of days, this is the bacteria concentration. And so what they're giving me, this is a x variable, so I just need to fill in an x variable. And they did say function, so I guess I should say f of x instead of y. I know I'm being a little lazy with that. Technically, that's the function notation. So I guess I could say f of 4.5. So I'm filling in 4.5. If you want to do 2 to the 4.5 by hand, bless your soul. I don't know what to tell you. It's not something I would be doing. Definitely grab a calculator at this point. And you should figure out it's something about like 33.9. And then we're talking about that crazy unit of measurement that they have, which is million bacteria per milliliter. Million bacteria per ml, right? Something like that. Any questions about this or where those numbers are coming from? So like we talked about linear, we had that y-intercept was like an initial amount. So now this c is like our y-intercept. If they give you an initial amount, that's what they're talking about, right? So if they give you an initial amount, that would be your c. If they give you the rate of increase, here they say it doubles, so the rate of increase is 2. I'm hoping you can take something verbally like this and create a formula. And then after you create a formula, if they give you an x or y variable, hopefully you can go and plug that thing back in, right? Okay.
I have a quick semi-related question, not about this, but our final in this class Is it going to be just like all the other tests where you give us the review and the test looks like the review?
So for the final, the best thing I think I could say is to study your test. Because I'm going to take stuff basically that was on your previous test and kind of compile questions from those things is pretty much what I'm going to do.
Okay, so we can treat the old test like the review, basically, is what you're saying.
Yeah, that's pretty much what I do for that. You may not
Okay.
get your test 4 back before the final, and if that's the case, then study your quiz 4, because I mean those things align pretty well anyway.
Okay, thanks.
Yep. But there will be a little bit of new material on the final as well. The stuff that we cover between test 4 and the final.
Is there going to be any review for that? Is there going to be a quiz on this stuff, the new stuff?
On the stuff that we cover in between, God, I have to look at it. I mean, I can hold class and take questions in, but I wouldn't plan on creating its own little separate review or anything.
Okay.
Yep. So these are the facts that we talked about earlier. How to obtain g of x from f of x. Okay, so this goes back to those graph transformations. So if we have this as our parent function, if we take this, you might notice that +1 is happening to your x value. So if we're adding 1, and we're thinking about x's go left to right, you would think it probably goes right, but in actuality, this thing is going left 1 unit is going to be the shift, right? And then the other one, if we see this, we can kind of look at like this thing happening first. We're going to do the 2 to the x. And then after we do the 2 to the x, we're going to put a negative on it. And so it's kind of like we're taking the y value that we had here and throwing a negative on all the y values. And so if we're thinking about that, everything that's up here is going to come down here, and everything down here is going to come up here. And so we're going to do a flip. This is going to flip it, or I guess the more technical term they use in the book is reflection. So this is a reflection across the x-axis. Okay. So this is all coming from the things that we previously learned with like functions and graph transformations and graph shifts. Now they're just applying it to this guy as a parent function, 2 to the x. And so if it's happening up here in the exponent, it's happening to the x's. If it's happening down here in the ground, it's happening to the y values. Okay. Okay, now we get into compounding. Suppose you have a principal of 1,500 and the interest rate is 7% compounded annually. Calculate the balance after 10 years. Okay. I want to think about this a little bit. But if I think about just the first year, if I want to think about how much this is going to earn, so it's going to earn, in interest, it's going to earn 7% of 1,500. And so this is the interest. And if we were to calculate this, we would take the interest and we would add it to how much we initially had in the account. And so this is kind of silly, but if I want to think about that, I can think about this as being one of the 1500s, and I'm adding 0.07 of them. There's another way I can sort of write this. These both have a factor of, what, 1500? And if I pull out the 1500, I'm left with 1 plus 0.07. And so if we're going to add 7%, another way to think about that is that we have an increase of 7%. The other way to think about that is you're doing 107% of your original thing. And if we do that, I have that number in my notes. Let me check it right quick. 1605. And so if you want to think about this year to year, we could do this 10 times if we really wanted to. I don't want to do that. I want to come up with some sort of formula. We're going to take that 1605 and we're going to add 7% of the 1605. So each year, our total in our account is going to increase, and therefore each consecutive year, the number that we're working with is going to increase. And so if we're doing this, we're going to do 1605. We're going to do one of those plus 7, or we can think about it as 107% of this thing. Okay. And if I really wanted to, this is kind of silly. I could calculate, well, let me crunch this number right quick. What do I have in my notes? 17.35. So if I want to figure out this number, crunch it, it should be 17.35. The 1605 to the 1.07, it might seem silly, but instead of writing 1605, I can write 1500 to the 1.7. And if I do that, you might notice a pattern starting to develop here. Is that we have this thing happening twice in year 2. You could probably guess. But in year 3, you're probably going to get that 1500, and you're probably going to get that 1.07 happening 3 times, right? So we're going to 107% this thing 3 times is what this kind of saying. Or I could write it as, what, 1500 and 1.07 to the, ooh, not x, to the 3rd, sorry. Getting a little bit ahead of myself there. Okay, and if we figure that out, did I figure that out in my notes? It's not right. No, I didn't. Okay. 1500, 0.07 to the 3rd. This should give you something like 1837.56. Okay. And so if we want to find a sort of general formula, you might notice, how do they do it in your book? Let me try to keep it consistent. Okay, so they're using A and P and R and T. Because there's 2 different books that I've used to teach this, and they use different variables. So A, they're going to say, is the accumulated amount. So if we want to figure out the accumulated amount, or the account, our account balance after 10 years, or after X years, I guess, this 1500 is coming from something called the principal. This 1.07 I'm getting from 1 plus my interest rate. And this 3 they're getting from the time of the year 3. And so in general, this is sort of what the formula is going to look like. And let me talk a little bit about this again. This is the accumulated amount. This is your final balance after so many years. This is P, the principal that you start out with. This is R, or your annual interest rate. And T is the number of years or the time. And so we use this formula. We're going to do 1,500. We're going to do 1.07, and if we want to figure out for 10 years, we have to do it to the 10th. What is that? 295073, I believe. And we're talking about dollars. And so this is how you sort of find compounding interest, right? If it was simple interest, we would just do this 1,500 times the 1.07 once, right? But we're going to compound it, and they're going to compound it each year. We have to use this sort of formula because kind of a little vocabulary check. The difference between simple and compounding interest is that when you have simple interest, you're just taking the interest on your principal, right? But when we have compounded interest, you might notice we're getting what, $105 from our interest here. We're taking that 105 and we're doing interest on our interest, right? Is the kind of the difference between simple interest and compounded interest, is that when we're doing this, we're actually taking interest on our interest. And so this thing is going to go up a little bit faster than just doing it simple, right? So we're compounding once per year. Our formula should look something like this. Okay. So suppose $2,000 is deposited by a 20-year-old worker in an IRA that pays an annual interest of 6%. Describe the effect on the balance after 30 years at the age of 50 if the interest were compounded quarterly instead of annually. Okay. So the first thing we want to figure out is what would this be if it was compounded annually? And so we've just figured out that formula. And so if this is compounded once per year, he's going from 20-year-old, so we don't really need to know how old he is. We don't really need to know the 50. What we really need to know is he went for 30 years, right? And so that 50 and that 20, if you want to mark it out, it's kind of extraneous here. The thing that we need to know is the time of 30 years. We need to know an interest rate of 6%. We need to know a principal of 2,000, and I think we can fill everything into this formula. So my principal was 2,000. I'm doing 1 plus my rate. And so I hadn't really explicitly said it, but you have to convert these things to decimal, and you have to convert them appropriately to decimal. And so 6 should be 0.06, and we're going it to the T, which is the 30 years. And so if you're doing PEMDAS, like the first thing you should do is add those two numbers on the parentheses, right? And so now I'm grabbing my calculator to do 1.06 to the 30. And then I'm multiplying that by 2,000. And I'm getting 11,486.98. And so this is if it's compounded, what, annually? And so we want to talk about this thing being compounded. Being compounded means is I figure out the amount, right? And so each year, like when I did this one, I would actually like figure out the amount for that year. And I would go year by year and crunch the numbers and figure out the amount. And then each year I would use the previous amount that I found to find the next year's, right? And that's sort of like what we're doing here. We're crunching the numbers every year. And so compounding is kind of referring to like how many times are you figuring out or crunching those numbers, right? And so if we do it quarterly instead of annually, there's basically two sort of things that happen to this formula that we have to change. And first thing is that you're not going to have an annual rate. You want to find the quarterly rate. And so if we want the quarterly rate, we want to do R divided by N is what they say, where N is the total number of times you're compounding per year. And so if we're doing quarterly, we're compounding this thing 4 times per year. That's what quarterly means. And if I do 0.06 divided by 4, I have this in my notes somewhere. Let me scroll on down. 0.015. So I have to find the quarterly rate. The other thing I need to know is the total number of times it gets compounded. And if I'm compounding it n times per year and I'm compounding it for t years, you might figure this out, but it should be the number of times you compound times the number of years. And so if I'm doing it quarterly for 1 year, it's going to do what? 4 times 1, it's going to be 4. If I'm doing it quarterly for 2 years, I'm going to have a total of 8 compounds. So I'm doing the total number of compounds per year times the number of years gives me the total number of compounds. So NT here, so if I'm doing it quarterly, and then the time here, I'm doing it for 30 years, you might figure this out, but there's a total of 120 different compounds that are going to happen to this thing. We're going to compound this thing 120 different times. And so if you're figuring this out more, or if you're crunching these numbers more, do you think this amount is going to go up or down? I guess is my next question. Well, I guess it's probably going up, I'm thinking. Who knows? Let's figure it out. So A equals P. If I want to change around the formula, I can a little bit. I did my R over N this time. I did my NT up here. And so this is how my formula looks different if I'm compounding it N times per year. So it's the same as the previous formula. The only thing we change is the rate. We've got to change our annual rate to our quarterly rate. And we've got to change this to reflect the total number of times it gets compounded. Whew. Okay. So now just filling in everything else. My principal is what, that 2,000. I have 1 plus 0.015. And I have NT gives me 4 times 30, or I'm just going to fill in the 120. And this, now I'm grabbing my calculator. Did I leave enough room? Maybe a little bit. Nope. But if I want to figure this out, it should be giving me something like getting 11,938.65. Okay. And let's just like reemphasize. I believe this is going up by 451.67 is what I have in my notes. And so it went up by about what, $451, which isn't bad, but you're also like thinking about this is only 6% and it's over what, 30 years, so that's not a whole lot of money for 30 years, but it is only 6%, right, annually. Okay. So if we compound it once per year, it's going to be this amount. If we compound it 4 times per year, it'll be this amount. I guess my question is like, well, how many times can we compound it, right? We're always like, we're always like the annoying mathematician, like, you know, everyone else goes to 10, but we always want to go to 11. Always crank it up like one more. So if we do it like once per year, 4 times per year, can we do it 10 times per year? Can we do it once a month, 12 times per year? Would be what? 12 times per year. Can we do it once a day, 365 times per year? You want to wake up each day and just crunch those numbers and see how much is in your account? So this is coming from compound interest. So I want you to have this like question in the back of your mind. Well, how much can I compound this per year? How many times is the maximum amount of times I can compound this per year? And so in order to talk about that, we've got to introduce this thing called Euler's number. And if you see this, I know his name looks like Euler or something like that. It's pronounced Euler, like the Houston Oilers or something like that. I used to mispronounce this like for the longest time. And it's a really common thing to mispronounce. It's kind of funny. So this was a modified formula we came up previously, a previous problem. Now we're talking about E. So if you notice, there are 2 different E's on your calculator. If we do this one, that's going to do the scientific notation. So if we go to second E on this one, it's going to do scientific notation. The other one you want to find is right around here. And so if we hit second E, it brings up E. I could do E to the first power. That's going to give me the number for E. So that's what my E is representing, 2.718. Euler came up with this crazy number. It comes up in nature all the time. We see it in nature, so we can kind of treat it like a unit, just like, you know, pi is its own thing. We can talk about E as being its own thing. And so we have the function f of x equals e to the x is the natural exponential function. So this looks like something with the base of 2.718, right? Is about what it looks like. It's an exponential function with the base of around 2, right? Almost 3. And so let f of x equal 2e to that, okay. Approximate the following to 3 decimal places. And so we want to figure out 2e to the minus 0.05 times 1.2. And so this is basically a calculator check sort of problem. And we want to find 2e to the minus 0.05 times minus 4. Can you pull out a calculator? Can you do order of operations in the correct order? So e to the 0.05 times 12. E to the negative of 0.6. Is it 0.2? And do I have this in my notes? I'm getting 1.884 for this one, and I'm getting somewhere around 2.443 for this one. Is that right? No, that's wrong. My notes are wrong on that one. Okay. So this one should be 1.0976. This one should be 2.443. That one's correct. Any questions about this? Okay. So we're sort of leading to this thing. How many times can I compound this thing per year? And this is where we're getting at. We can do it. We can keep on increasing this number, this n. And if we keep on increasing this n, you might notice that this sort of formula is reaching a sort of limit here as we increase the n. And as we increase the n, that thing is going towards basically the natural exponential or Euler's number. And so our formula for this is going to look like the PERT formula is what some people call it. There's a shampoo out there called PERT. I like try to mention it like a couple years ago, and like most of the class actors like they didn't know what I was talking about. So I don't know if you know what I'm talking about, but there's a shampoo out there called PERT. And so some people memorize this as PERT, but this is continuously compounded. So this is like we let our n go to infinity. So it's like we're compounding this thing, or we're crunching this number infinitely many times per year. We keep on getting it smaller and smaller, right? Okay. And so you might notice if I say that out loud, it's not something you're actually going to be able to like physically do. It's something that's very sort of conceptual, right? We're not actually going to be able to infinitesimally sort of figure this thing out. But it reaches a limit, right, is the important thing. And that limit is Euler's number. I think, where am I at? This thing right here. As you let n go to infinity, it's approaching e to the r is what happens. Okay. And I think previously, if I can remember correctly, I don't expect you to memorize like these formulas. I expect you to know what the letters mean, kind of. I'm not going to tell you like this is principal, this is the rate, this is the time, but I will probably most likely, from what I remember, I will give you the formulas on the test or anything like that that you have. I'm not expecting these to be like sort of memorized. Where am I at? Am I on number 8 now? Is that where I'm at? Okay. We're getting down there. So, key word here, the first thing like I want you to sort of realize is this word right here. And the second it says continuously, like I want you to like get in your head, as soon as it says continuously, the thing that makes my hair look continuously smooth is the PERT. So PERT is what you use for continuously compounded. If it says anything else, if it says quarterly, we're going to use that really complicated one. If it says annually, we're going to use that first one that came up. And ooh, that might be worth like mentioning. If we take, I believe it's on here. I didn't like say this, so it might be worth like mentioning explicitly. But if I take this is compounding it n times per year. If I let my n be 1 and I compound it 1 times per year, guess what formula you get out of this thing? You get that formula back, which is the thing that we had on the previous page. So technically, that other formula follows from this one. I know we learned this one first, but this one kind of follows from this one. If you let n be 1, it is the same formula. That previous one was just a very special case. That's just a very special case where n is 1, right? Okay. So they didn't say compounded annually. They didn't say compounded quarterly or monthly, which would be 12, right? So how do we do this? It is compounded continuously. So if you don't have a calculator for this test, you're probably going to definitely need one to at least be doing these Euler's numbers. Principal of IRA is 2,000. So the first thing we're filling in is principal. The principal is 2,000. My E is just an E. I'm doing to the RT. So R is my rate, which is 0.06. And I want to multiply that by time, which is 30. So this is still, I believe, the same numbers coming from the previous problem. So we did a few problems to see if you could crunch this thing. But if we do 2,000 and we're doing what, E to the 1.8, I believe. This is going to give me 1299.29. My internet connection is unstable, apparently, is what it's saying. So if I get cut, I will be coming right back. I don't know what to tell you about that one. But it did just give me a warning on Zoom for some reason. My internet connection's not stable. Who knows? I have Google Fiber. It shouldn't be an issue. Okay. Questions about this? It's pretty much just take this formula, plug in your principal, knowing that this is your principal, knowing that this is your interest rate. Oh, we got to convert this rate to a decimal. This is my time in years. Got it. And you might notice there's no N in this formula anymore because our E is kind of taking place of that N, right? So we don't need to worry about any other numbers, right? Okay. So the table lists the concentration of a sample of E. coli bacteria in billions per liter after X hours. Find the values of C and A so that it models this. And then estimate the bacteria concentration after 2 hours. So if we want to figure out our C, right there. Now we just need to figure out what our A is going to be. Let's see how I did it. Yeah, so you have a few options of what you want to pick. We could pick this. It's going to give us an exponent of 3. This is going to give us an exponent of 5 or an exponent of 8. I like to do things the easiest way, typically. So if we pick the next largest numbers, that's the way I'm probably going to go about doing things. Pick the smallest numbers possible, right? And so if we do that, 6.2 is equal to 0.5 times A to the X, which is 3 here. Woo. We might be going into new territory because we hadn't talked a whole lot about cubes. So this is 0.5A cubed. I have to divide each side by a half, or this is the same thing as multiplying it by 2. So this should be what? 12.4 is equal to A to the third. And if I have A to the third is equal to 12.4, the thing I want to do to get rid of that third is to take a cube root. So A is going to be the cube root of 12.4. And so at this point, I'm hoping you're grabbing a calculator, and I'm rounding this, so I'll write the little squigglies. It's approximately 2.315. And maybe we got a little bit of time, I could show you all this. If you want to do this in your calculator. I think the easiest way to do this, or the easiest way to find it, is to go to math. Where's math? Math. And your cube root is like the fourth option there. So they have cube roots. Anything higher than a cube root, you're gonna have to like plug in the number, right? So, but if we want to do a cube root, we can do it 12.4. 2.315 is where I rounded that, right? Okay. And so I think we have everything we need to fill in this number. So my function looks like f of x. My c looks like it is 0.5. And my a looks like 2.315, and I'm raising this to the x. And so this is my function for part A. Part B, they're giving me 6.2 hours. That should be a x quantity, because my other quantity is telling me how many, what is it, billions per liter of bacteria that I have. And so if I want to do this, I want to plug in for part B, I want to plug in 6.2. So I'm evaluating this function at 6.2. So maybe as we're talking a little bit about order of operations, but I have to do exponents before I do multiplication. I have to do that thing first. 2.315 to the 6.2. I'm getting something like 182.06. And then if I multiply that by half, I'm getting something like 91.03. And then maybe a little bit of interpretation. We're getting this as our function value. We're talking about billions per liter of bacteria. And so maybe like interpret it a little bit. After 6.2 hours, there will be 91 billion bacteria per liter. And this is kind of like a foreboding, however you want to interpret it. But like, these are exponential functions. Work with these things. Do your homework on exponentials, and do it before, I believe next class is where we start talking about, logarithms. Work on these things before next class. Like, get these in your brain. Work with it somehow. Math is a contact sport. You've got to be active, and you've got to do it by yourself, right? You've got to try things out by yourself. Work with these things, because next class we're going to talk about logarithms, and as much as you know or don't know about exponentials is going to be the same thing that you either know or don't know about logarithms, because logarithms are, I'll give it to you, they're the inverse of exponentials, basically. That's how we're going to define them. That's how we're going to look at them. So if you look at exponentials and you get a feel for how these things are operating a little bit, it will give you a little bit more ammo into tackling the logarithms, right? Questions? I always feel a little bit like I always feel like I'm like going to become David S. Pumpkins and just go, any questions? This is like horrible. Nope.
When is the written homework due?
The written homework for this, so there was nothing due this week. There will be a written homework due next week, Tuesday, I believe.
Okay.
I
Over
don't
this
think,
section and Thursday section.
yeah, over 5.3 and 5.4.
Okay.
Wait, this is due next or this Thursday?
No, next Tuesday,
Oh, okay.
the written work will be due.
Okay.
And I'm not sure if I've even set that up for y'all yet, but that will definitely get set up this week.
By the end of the day, next Tuesday?
Yep.
Or by, okay, cool.
Well, we got 3 minutes. We can look at this right quick. I'm just going to look at this first one, and I will go back over it. But we're looking at these, and this is going to lead into logarithms. And it probably wouldn't hurt to get a little head start on this one, because this section is a little bit long. But you might notice we're multiplying by 10, and so this looks like a exponential function. Where my c, I believe, is 1, so I don't even really need to worry about my c too much. But basically, this looks like a 10 to the x function. Okay. And hopefully that makes a little sense. If I do 10 to the minus 1, that's going to be 1/10. 10 to the 0 is going to give me 1. 10 to the first is going to give me 10. 10 squared is going to give me 100, right? And so we're doing this sort of base 10 sort of thing. We like to do things in base 10 for some reason. Probably has to do with those digits. This, if we look, is like I took my x and my y and I flipped the things. And so this thing, I've talked about it a little bit, but this is what our log function, and this is a log base 10. And so we want it, and so this is like saying 10 to the what power is going to be 0.1, or 10 to the what power is going to be 1. Well, 10 to the 0 power will be 1. 10 to the what power will be 10. Well, 10 to the first power will be 10. 10 to the what power is going to be 100. Well, that would be if 10 was to the second power. So now we're thinking about things kind of backwards from what we think about things with exponentials. And I wrote this as log base 10, but really it's a common logarithm. I really don't have to write a base on there. And this is leading into what logarithms are going into. So another way maybe to think about that is what was the exponent when it was a base 10, right? Is another way to ask this question. Well, what was the exponent if it was a base 10? Same thing here, right? We're thinking about things backwards. Instead of plugging in an exponent and crunching the numbers, we're thinking about it backwards or thinking, well, what was the exponent? And so we'll go a little bit more into that. We'll go into the other definition, that definition next time. But I think we're right there at the end of the class right now, huh? Okay, so are there any questions? I guess I'm gonna go ahead and hit stop on the record.